Hello there. This video is mostly for Eric in my Discrete math class. Hopefully you're safe and healthy and mostly just sitting around home bored. I chose to start this video with a picture of me when I was on vacation out in Oregon right before school started. And since in class we've been learning about logic and the difference between valid and invalid reasoning, I also found an appropriate quote and put that in here too. I want to first review the different kinds of invalid reasoning that we talked about last week at the end of the week. First, we talked about converse error, where you had an if-then statement and you wrongly assumed that it would still make sense if you went backwards. You knew P implies Q, you tried to assume Q implies P. Your book's example of this looks like this. It says, if a person has not done anything wrong, then he is cleared at the end of the investigation. I was cleared at the end of the investigation, therefore I have not done anything wrong. The problem with converse error is that you might have done something wrong, but it wasn't what they investigated. There's other things that could be involved as well, so you can't just turn it around and go backwards. That's converse error. The second kind of invalid reasoning we looked at was what was called inverse error. That's where you try to make both halves negative. You know if P then Q, you try to assume if not P then not Q. The book's example for this one says, if a person is a member of the Spanish club, then the person speaks Spanish. William is not a member of the Spanish club, therefore William does not speak Spanish. And of course, the Spanish club doesn't necessarily have everyone who speaks Spanish in it, and so he could just not like that club. And the third form of invalid reasoning was improper induction. What that one said is that you know that there is a situation where P of X is true, but you wrongly assume that for all possible situations P of X is true. Your book gives this example. They have some function where they evaluate f of 1 and get 1, they evaluate f of 2 and get 2, and they evaluate f of 3 and get 3. So they make the claim that this is going to always give the number you put in for all positive integers. And all you have to do to show that's wrong is find one situation where it doesn't work out. You can see on the screen that if you plug in 4, you don't get 4, and so it doesn't work for all positive integers. Now, of course, earlier last week we also learned three kinds of valid reasoning. The law of detachment, where you knew an if-then sentence, you knew the if part was true, so you could say that the then part would definitely be true also. Transitive, where you had a bunch of if-then sentences that all led into the other, and you could go from the if part of the first one to the then part of the last one. And finally, indirect reasoning, which was the same as the contrapositive. You had if P then Q, so you could conclude if not Q then not P. I mention those because both valid and invalid are going to come up in the problems we're going to go through. What we're going to do Tuesday in class is look through a bunch of problems together, and so basically in this video I'm going to go through those problems with you. These happen to be on page 59 in your book. I don't know if you have your book or not, so I scanned these and we're going to look at the problems and see what's up with them. What you probably will want to do is to pause and think about what the answers are before I go on to the next frame and tell you what those are. So the first several problems that we're going to look at, the directions say identify the type of argument and tell whether or not it's valid. So it's going to be one of those 6 things we talked about that could be either valid or invalid reasoning. And the first example says the sine of 30 degrees is the square root of 1 over 2, the sine of 45 equals the square root of 2 over 2, the sine of 60 equals the square root of 3 over 2, so therefore the sine of 15n degrees equals the square root of n minus 1 over 2 for all integers greater than or equal to 2. And again, after each of these, you might want to pause and think about what the answer should be. So the fact that we've got a whole bunch of examples and then it tries to generalize that to n, that's a dead giveaway for improper induction. Just because something happened 1 or 2 or 3 times doesn't mean it's always going to happen. So it's improper induction, invalid. The next problem says if you buy a ticket to the concert, you will go. You don't buy a ticket to the concert, therefore you don't go. This one is inverse error. They're trying to make both parts of it negative. And the reason why that is invalid is there could be other ways you get to go to the concert besides having a ticket. Maybe you won a free ticket. Maybe you're in the band or on the crew. There's lots of ways that you could be there without having to buy a ticket. Next up, we have the question, if a person does not register to vote, then the person cannot vote. John can vote, therefore John has registered to vote. So this one actually is a valid argument, which sometimes takes people by surprise because most of them in this section are invalid. But here, they've turned it around and made it negative. They do the opposite of the then part, he can vote, so they conclude the opposite of the if part. He must have registered to vote. And that is indirect reasoning. It's the contrapositive, and that is perfectly valid. Next it says, if this is a presidential race, then education is a top issue. Education is a top issue, therefore this is a presidential race. This time they're trying to go backwards, but it's not negative, and that would be converse error, which is invalid. So number 9 here says, for all real numbers x, if x is greater than 2, then x squared is greater than 4. For all real numbers x, if x is greater than 3, then x squared is greater than 9. Therefore, for all real numbers x, if x is greater than n, then x squared is greater than n squared. Again, these separate lines where it starts with specific numbers and then they throw n in there, that's kind of the dead giveaway for improper induction. Sometimes the fact that they all say for all throws people off because the first part of improper induction has like a there exists in it. But what we're saying is that there exist 2 specific cases where this works, and we're trying to assume that it works in every possible case. And it is improper induction, which is invalid. Next up it says, given the conditional if P then Q, or P implies Q, we're supposed to do 3 things. We're supposed to write the converse of that. We're supposed to write the contrapositive of the converse. And we're supposed to figure out whether the contrapositive of the converse is either the inverse, the converse, or the contrapositive of the original statement. So again, you might want to pause and think about those 3 questions before we look at the answer. Again, here we're starting with P implies Q. Converse means you go backwards. So the converse of that is going to be Q implies P. Then we're supposed to do the contrapositive of the converse, which means I take my answer to part A, I turn it around, and I make it negative. That's why it's going to be not P implies not Q. And this time, if I compare that to the original, what's up is it's negative, so that's why it ended up being the inverse. So it turns out that the converse and the inverse are contrapositives of each other. On number 11, they give us this example that says, assume Peter has an answering machine attached to his telephone. He turns it on whenever he's leaving home. When Sarah called, she got the message on the answering machine. Sarah concluded that Peter was not home. We're supposed to again figure out what kind of argument she used to draw her conclusion and then say whether it's valid or invalid. So basically, if I turn this into if-then statements, we'll start off by saying, if Peter's not home, then the answering machine's on. And what happened is she figured out the answering machine was on, so she concluded he wasn't home. And the problem there is she's trying to turn things around backwards, which is converse error. She's doing like if Q then P, and that doesn't work. So it is converse error, invalid reasoning. So next up it says, given the following argument, for all x equals 3 implies x squared equals 9. Then x is not equal to 3, so the conclusion is x squared is not equal to 9. We're supposed to write the form of the argument and figure out whether it's valid or invalid. Now, sometimes when people will see the for all there, they immediately want to jump on improper induction, but that's not what this one is. What's going on here is inverse error. Basically, it says if one thing, then another, and what they're saying is not the first thing, so not the other. And that ends up being two knots. That is inverse error, and it is invalid reasoning. I always get kind of a laugh out of the next problem. It says, for all persons P, if P is President of the United States, then P is at least 35 years old. Queen Elizabeth II is at least 35 years old. Therefore, Queen Elizabeth II is President of the U.S. And we're supposed to figure out the form of the argument. It asks us whether the premises and the conclusion are true, and figure out whether this is valid or invalid. Now, they mention a couple of terms here that I didn't specifically define last week. Premises are just the arguments that go into making a conclusion. Here, it's the facts that to be president, you got to be at least 35, and Queen Elizabeth is at least 35. Those are the premises, and they do both end up being true. The conclusion is what comes after the therefore, and that would be Queen Elizabeth is the president. That's rather obviously false. What's going on here is converse error. Again, they are trying to conclude the if part by starting with the then, and that doesn't work. So yeah, it is converse error, it is invalid. So the next problem, we're still trying to figure out what's going on and whether it's valid or invalid, but it's a much longer argument. What it says is, if the land is covered with ice, then the land is Antarctica. If the land is Antarctica, then there are research stations there. If the land has research stations, then scientific study is being conducted. Scientific study is being conducted on the land, therefore the land is covered with ice. So think about that one for a minute and see if you can sort out all the different things that are going on. So what's weird about this problem is that really there's both valid and invalid reasoning happening at the same time. They have transitive going on, which you can tell by the fact that there's a whole bunch of if-then sentences, and one of them leads into the next, which leads into the next. But there's also converse. They start off with the end of this, and they end up going back to covered with ice. And so one of those is valid, one of them's invalid, and a real obvious question might be, what do you do when both of them are happening at once? Well, anytime any part of an argument is invalid, it spoils the whole thing. And that's why overall this is going to be invalid reasoning. The transitive part's fine, but because they tried to use converse, it's going to end up being invalid. Now, you could also argue that some of the premises they started with weren't really true, because there's places that are covered with ice that are not Antarctica, but that's a completely different issue. Here, converse is the main reason why this is going to be invalid. Here's a fairly similar one. It says, if you send a minimum order of $10 to a mail order house, then your name's put on a mailing list. If your name's on the mailing list, then you will receive many catalogs in the mail. You received many catalogs in the mail, therefore you've sent a minimum order of $10 to the mail order house. That's really almost identical to the previous problem because it's got transitive going from one if-then statement to another, but it also has converse because they're jumping backwards. And again, if anything about the argument's invalid, the whole thing is, so this is invalid reasoning. I am actually purposely doing these out of order, and the next one that we're looking at, it says if x is a real number, then x squared is greater than or equal to 0. If x is an imaginary number, then x squared is less than 0. 2i is an imaginary number, therefore 2i is not a real number. Again, you want to kind of think what all is going on in this problem. And once again, there are multiple things happening, but if you look carefully, it really is different than the two problems we just got done doing. It's not just like transitive and converse, there's some other stuff here. So I'm going to start here by looking at the second statement. It says if x is an imaginary number, then x squared is less than 0. So they tell us 2i is an imaginary number. And by detachment, I can conclude that x squared has to be less than 0. So now I can take that and I can look at the first statement by transitive, and I can turn that around and make it negative. I know x squared is less than 0. That means x squared is not greater than or equal to 0. So the if part means it must not be a real number. And we really have all three of the forms of valid reasoning that we talked about going on at the same time, but they are all valid, so yes, it is a valid argument. And we're going to quickly look at two other questions, which are back at the beginning of this section. And it says we're supposed to indicate whether these are true or false. One of them says if an argument is invalid, then it must have a false conclusion. And the second says if a given conditional statement is true, then its inverse must be false. And it turns out that both of these are false statements. Just because an argument is invalid doesn't mean you have to have a false conclusion. You could come up with a bunch of BS but still have the right answer. You've probably done that on tests before. And it doesn't mean that you thought through the process right, but your answer could actually still be correct. And again, just because you have a conditional that's true doesn't mean the inverse is going to be false. In fact, if you had something that would make sense as an if and only if statement, then it would have a true inverse also. So, yes, the falsehoods that we came up with are not good arguments, but they don't necessarily lead to false conclusions. They just could. And so that's this whole section, so you kind of have a clue of where we're going with things. We'll have one other section I'm going to make a video for here which deals with other kinds of reasoning. We'll take a look at that. Then you're going to be doing some problems in the chapter review and on a review worksheet, and eventually we will be getting to the chapter 1 test, which, depending on whether you're home or not, we'll figure out exactly how we're going to make things work with that. But that's where we're at in this section, and we'll call it good for this video.